This is a networking lab demonstration.
Today, I'll be demonstrating a foundational networking project I built using Terraform on AWS. The purpose of this project is to show how we can use infrastructure as code to build a virtual private cloud, or VPC, with both public and private subnets, an internet gateway, a NAT gateway, and EC2 instances. Along the way, I'll also explain how security groups and security group rules work, since that's one of the most important networking concepts in AWS. Let's take a look at my Terraform code file.
I'm setting up the provider and generating SSH keys. This step is critical because it establishes how Terraform communicates with AWS and ensures I have secure access to the resources I deploy. Here, I define my AWS provider. The provider tells Terraform which platform I'm working with. In this case, it's AWS. I also specify the region, US East 1, so that all of the resources I create will be deployed in that specific region. This is important because AWS resources are region-specific, and costs, availability, or even networking features can differ between regions. Next, I use the TLS private key resource to generate a new SSH key pair. I'm using RSA with 4096 bits, which provides strong encryption. Instead of manually generating keys on my local machine, Terraform handles this for me automatically, which makes the setup repeatable and secure. This private key will allow me to authenticate securely when connecting to my EC2 instance. Here, I create an AWS key pair resource. This takes the public portion of the SSH key that was just generated and registers it inside AWS under the name SSH key. This is how AWS knows which keys are allowed to connect to my EC2 instance. Essentially, Terraform is bridging the gap, generating the key locally and then securely uploading the public part into AWS. Finally, I save the private key locally in a file called Terraform key. This file is what I'll use when I connect to my EC2 instance over SSH. By managing it in Terraform, I make sure the key that AWS is expecting and the key I have locally always match. One important note, since this file contains a private key, I need to be very careful with file permissions and security. Storing it securely is critical to avoid unauthorized access.
The next section of my code covers VPC creation. I start by defining the VPC. This is my private isolated network inside AWS, and I've given it the CIDR block 12.0.0.0/16. That means I have about 65,000 private IP addresses to work with inside this VPC. Everything else I build will live inside this container. Next, I define two subnets. The first is the public subnet, which has a range of 12.0.1.0/24. Any resources here can connect directly to the internet if routing is configured. The second is the private subnet, which has 12.0.2.0/24. Instances in this subnet don't have a direct path to the internet. Instead, they use a NAT gateway for outbound connections. This separation is a best practice for secure cloud design. Now I need connectivity. The internet gateway allows resources in the public subnet to communicate with the internet. For the private subnet, I use a NAT gateway. This lets private instances initiate outbound connections. For example, I can download software updates without being directly exposed to inbound internet traffic. I associate the NAT gateway with the public, not private subnet. That way, it will have access to the internet gateway. Now, I need to configure route tables for my VPC. Route tables are critical because they determine how traffic moves in and out of subnets. Here, I'm creating a route table for the public subnet. Notice the route. It points all outbound traffic, represented by 0.0.0.0/0, to the internet gateway. This means instances in the public subnet can communicate directly with the internet. Next, I set up a route table for the private subnet.
It also points outbound traffic to 0.0.0.0, but instead of using the Internet Gateway, it routes traffic through a NAT gateway. This is important because it allows instances in the private subnet to reach the Internet, for example, to download updates, without being directly exposed to inbound Internet traffic. Finally, I associate each subnet with the right route table. The public subnet is linked to the public route table, and the private subnet is linked to the private route table. Without this association, the route tables wouldn't apply to the subnets.
Now let's look at how I configured security groups in Terraform. Security groups act like virtual firewalls for our EC2 instances, controlling which traffic is allowed in and out. In this project, I set up two main security groups, one for the public Bastion host and one for the private instance. Let's break it down. This first security group is for the Bastion host. It allows SSH access on port 22 so I can connect from my own computer. I've used 0.0.0.0/0 here, which means any IP address can connect. In a real-world environment, I'd restrict this to just my office or home IP for better security. I also allow ICMP traffic, which lets me use ping to test connectivity. For outbound traffic, I've opened everything, so the Bastion can reach anywhere on the internet. Next, I created a security group for the private instance. Notice that here, I haven't allowed any inbound rules directly inside this block. By default, that means nothing can connect in. Instead of opening the private instance to the world, I use separate security group rule resources to allow access only from the Bastion security group. The first rule allows SSH on port 22, but only if the traffic comes from the Bastion host. That means I can log into the private instance, but no one else on the internet can. The second rule allows ICMP for ping testing, again, restricted to the Bastion. This approach, using a Bastion host as a gateway, is a best practice in AWS networking. It keeps private instances isolated from the internet while still making them reachable through a controlled path.
Before I conclude the configuration overview section of my demo, let me quickly explain Bastion hosts. I previously referenced the term, but I didn't explain it. I'm using my public instance as my Bastion host. A Bastion host is a special instance placed in the public subnet that acts as a secure jump point. Instead of allowing the whole world to SSH into your private instances, you restrict those instances so they only allow SSH from the Bastion security group. Then you log into the Bastion first, and from there you jump into the private instance. This greatly reduces your attack surface.
All right, I've finally gotten to the section of my code which covers the EC2 instances. As previously mentioned, my network has both a public and private instance. Let's examine the code. The first resource here is the Bastion host, which is deployed in the public subnet. Let's look at the key attributes. The AMI defines which machine image I want to use. In this case, I've selected an Amazon Linux AMI ID. The instance type is set to t3.micro, which is a small and cost-effective instance type, good for demos or lightweight workloads. The subnet ID points to the public subnet that I've already defined earlier in my VPC setup. Because it's in a public subnet, it can be reached from the internet. The key name ensures I can connect via SSH using my pre-created key pair. The associate public IP address is set to true, which means this instance will get a public IP so I can reach it directly. Finally, the VPC security group IDs assigns the Bastion host security group, which defines what inbound and outbound traffic is allowed. So the Bastion host acts as the controlled entry point into my VPC.
In the final portion of my code file, I define an output block. Outputs in Terraform are essentially a way to display or export important information after resources have been created. They make it easy to reference values without having to manually look them up in the AWS console. Here, the output block is named EC2_info. Inside, we've created a small map that collects 3 key pieces of information. First, the Bastion public DNS, which is the DNS name automatically assigned by AWS to the Bastion host. This is useful because it gives us a friendly host name we can use to connect over SSH instead of remembering an IP address. Next, the Bastion public IP, which is the direct public IP address of the Bastion host. This is helpful when you want to test connectivity, or if you prefer connecting by IP instead of DNS. Finally, the private instance IP, which is the private IP address of the instance that lives inside the private subnet. Since this private instance doesn't have a public IP, you can't reach it directly from the internet. Instead, you use the Bastion host as a jump box, and this private IP tells you exactly where to connect once you're inside the VPC. Outputs like this are incredibly helpful because they save you from digging through the AWS Management Console every time you need an IP or DNS name. They also make your Terraform project easier to share with the team, since everyone will see the same resource details right after running Terraform apply.
Now it's time to run the code. First, I'll show you my AWS console so that you can see that no infrastructure currently exists in AWS. I'll then issue the commands init, plan, and apply within the project directory where my Terraform file resides. Next, I'll return to the AWS console to show the running network. I'll end by testing connectivity. Watch while I wrap up this demonstration. Heading over to AWS console, I'll show you that I have no instances running. The only architecture currently set up in my AWS is AWS's default configuration. You get a default VPC and, I believe, a default route table.
Okay. Yes, notice that I have one VPC in North Virginia. That is my default VPC. Now that I've confirmed that my AWS is bare bones, I'm ready to execute the Terraform code. I need to be in my project directory. I will then issue my 3 commands, the Terraform init command, which will initialize my project based on the main Terraform file. Next will be the Terraform plan command, which allows me to confirm the configuration and flag to save if desired. Finally, the Terraform apply command, which will push the code to the cloud and build the infrastructure. I'll get started with the commands. I'll run Terraform init. The command was successful. Now I'll run Terraform plan. That command was also successful. It's just letting me know that I did not use the save flag. Lastly, I'll run the Terraform apply command. This might take a bit to complete execution, as my entire infrastructure will be built using this command. The command is interactive. I just need to indicate yes to confirm that I want to move forward with execution. The build is going to take a bit. I'll go ahead and fast forward this section. Awesome! The build is complete.
Next, I'll head over to the AWS console and do a quick walkthrough of my network, courtesy of Terraform.
Okay, see that I have 2 instances running. That would be my public and private instances. I have an elastic IP for my NAT gateway. I also have my added security groups.
Let's take a look at the VPC section of the console. Great! I have my non-default VPC. I have 2 subnets with additional route tables to match. I have a NAT gateway. My internet gateway is also set up. Take a moment and have a look. First, I need to SSH from my local machine into the public instance. Then, from my local machine, I will copy the Terraform key file from my local machine into my public instance. From my public instance machine, I'll change the permissions to the key file now copied to it so that it is more secure. Finally, I will SSH into the private instance from my public instance. All of this is necessary so I can remotely work between the machines as I test connectivity. Watch as I do just that.
Take note of my public instance's public IP address and my private instance's private IP address.
SSH into my public instance.
I see the problem. I need to change into my project directory and then retry the command.
Okay, I'm in. I'll now copy the key from my local to the public instance machine. Just making note of the correct public IP.
Okay, the file is copied.
Now I need to handle key file permissions. I change it to 400. This ensures only the owner, me, can read the private key. At last, I should now be able to SSH into my private instance from my public instance. I'll give it a try. Confirming the IP of my private instance. Perfect. I'm now in my private instance. Now that I can SSH into both instances, connectivity testing can begin. Since I'm already in my private instance, I'll test connectivity to the internet by pinging google.com. That's 8.8.8.8. Great! I've got connectivity to the internet. Now I'll have my private instance ping my public instance. Excellent! I have connectivity. Now I'll run the same test, but this time from my public instance to the internet, and then from my public instance to my private instance. Pinging 8.8.8.8 from my public instance. Awesome! My public instance has connectivity to the internet. Now I'll test its connectivity to the private instance. Perfect! My public instance can also connect to my private instance. That pretty much does it. I have a customized, fully functional network using infrastructure as code. This has been an exciting project to work on, and I hope you enjoyed seeing how everything came together. What really stands out to me is just how powerful Terraform is. The way it automates infrastructure and makes deployments so much easier is truly amazing. Thanks for following along. I look forward to building even more with Terraform in the future. I invite you to browse the playlist for similar demonstrations. Goodbye for now.